Hello everyone, this is Jaeun Porjeon. I am faculty member in the Department of Computer Science and Engineering at SKKU Seonggyungan University. Today I will deliver the talk about the IETF, I2NSF technology and open source project for cloud-based security service systems. This is the table of contents. First of all, I will explain software-defined networking SDN. And then, secondly, I will explain network functions virtualization NFV. Lastly, I will explain cloud-based security service systems. In the first part, I will explain deployment background and the framework of SDN, and also I will explain ONF activity for SDN standardization. And also I will introduce open source project for SDN. In the second part, NFV, I will explain deployment background and the framework of NFV. And also I will explain ETSI Edge standardization activity for NFV standardization. And then I will explain open source project for NFV. Finally, I will explain in third part cloud-based computing systems are explained, and then I will explain my main standardization activity in IETF, such as I2NSF. Finally, I will explain open source project for I2NSF. This is the terminology for cloud-related de facto standards, such as DMS, stands for Developer Management System. In other case, please read this slide. The first topic is software-defined networking SDN. First section, deployment background and the framework of SDN. As you can see, in the past, the networking is like a dinosaur based on hardware-intensive ecosystem. However, nowadays, networking is evolved based on software-intensive ecosystem. There is a big event, such as left-hand side is telco, telecommunication company. Right-hand side is a service provider, such as Google, Facebook, Amazon, Naver.com, Alibaba. So nowadays, this service provider want make their own network system and cloud, try to make independence from previous telco ISP. In the past, left-hand side shows the period of standardization. It takes 2 to 6 years, very long time. On the other hand, Google, Facebook, service provider want to shorten development period, like 2 to 6 months. In that case, those service provider, they are leading open source based project instead of standardization. The motivation of SDN, the first one is to allow network users to connect, also construct their own network protocols and test them easily. Such as Google, Facebook, they want to elevate the deployment speed of new services and product. The principle of SDN is based on SDN controller. SDN controller is a network brain to govern network configuration and the routing policy in a centralized way. This figure shows the ecosystem consisting of open innovation, software-defined networking, and network functions virtualization. This figure shows the architecture of SDN SDN. So left-hand side, there are 3 layers: infrastructure layer, control layer, and application layer. In the middle layer, SDN controller is connected to application layer, such as business applications, cloud orchestration, and SDN applications using northbound interface. On the other hand, southbound interface, such as open flow, standardized by IETF, network infrastructure components are configured by this interface, such as core network components such as routers and switches and the base stations in cellular network. The second subtopic is IETF, Open Networking Foundation Standardization Activity for SDN. So this figure shows the organization of IETF. The top decision-making organization is IETF board, having an executive committee. This IETF board has multiple sub-board and also team to standardize SDN-related works. And this figure shows the configuration of SDN controller and switch using southbound interface. SDN controller delivered open flow protocol-based control path is governed by this SDN controller, and open flow is actual protocol to control this switch or router in the network. The configured by this open flow protocol, and switch can forward using data paths based on hardware. This figure shows the example. SDN controller deliver configuration to open flow switch. Open flow switch owns and maintain its own flow table. Flow table has multiple entries. Each entry consists of the rule and action and statistics for that traffic. So this is the packet processing procedure. First of all, packet comes in SDN open flow switch, and then it look at its table. If there is no match, the packet will be delivered to SDN controller using secure channel. Otherwise, there is a match, apply appropriate action. In open flow or pipeline processing case, we can see multiple tables are interconnected in a serial way. So one packet comes in, processed by table 0, and then table 1, and etc. Table n can process in a serial way. So this shows the open flow structure I explained just before. So open flow entry consists of rule, action, statistics. The rule can be configured using MAC layer header information and also IP header and the TCP over UDP header information such as MAC address, Ethernet type, and also virtual LAN ID, the IP source destination address, and the payload protocol such as the TCP or UDP, something like that. And the action case, 4 cases: forward packet to an appropriate output port, or encapsulate and forward it to SDN controller if there is no match in flow table. And third one is drop the packet. Finally, send it to normal processing pipeline to other following table. The section 3, open source projects for SDN. So we have 2 projects. The first one is Open Data Line is for SDN controller. So it supports the open flow as a southbound interface, as well as other network protocols, SNMP, NetConf, BGP, and LISP. This website gives information to you and the source code for Open Data Line SDN switch. Secondly, Mininet is emulation open source project. So you can establish SDN network in your PC or laptop, and you can learn real kernel switch application code on top of Mininet. So please visit to this website. Second topic is network functions virtualization, NFV. Subsection 1, deployment background and the framework of NFV. So as you can see in the past, to provide the network functions, we use the middle box, such as DPI, PROS, GGSN, SGSN. Okay, also provide the edge, router, firewall, CG, NAT, and session board controller. So what is the major problem? The major problem is the demand from users is increasing, and this middle box is out of fashion. We take out and we purchase new boxes. This is a very expensive approach. So in the past appliance-based approach case, to upgrade the system or deploy initial system, in terms of CapEx and point of view, capital expenditure or operating expenditure OpEx point of view, very expensive approach. However, nowadays we can use virtualization environment, and we virtualize each network devices or security functions on top of virtualization foundation, such as NFV, network function virtualization. And then we can configure dynamically in terms of CPU, network bandwidth, and memory size. Sometimes we can scale down, sometimes scale up, depending on user demand. As a result, we can save energy, and also other resources reduction can be done to save money and time, energy. So motivation of NFV I explained. So KT in Korean ISP, AT&T is the United States Internet Service Provider ISP. They want to construct their own network services in the virtual environment using virtual machine. So the principle of NFV is NFV orchestrator like SDN controller governs all of network functions for network services running on top of virtual machines. So this figure shows, so to lower CapEx, capital expenditure, and OpEx, operational expenditure or operating expenditure, we can save money. So open source innovation, SDN, NFV, triangular, relationship is shown. This figure shows NFV architecture. NFV architecture case 3 layers. So the lower layer is NFV infrastructure layer. In the middle is VNF layer. Upper layer is network service layer. Okay. So each layer case we can see NFV infrastructure layer providing the based on hardware computing resources, storage resources, network resources are virtualized by virtualization layer. So each computing, each storage, each network, they are treated as a virtual resources. Using that 3 kinds of resources, we can construct VNF, a virtual network function, to run actual services. Network service layer case, we can connect with multiple VNF using a service function training. We can provide actual network service. So this figure shows one virtual network function can have one virtual network component, or we can make more component. And also VNF can be interconnected using service function training. So IETF developed the service function training, how to interconnect VNF functions. Subsection 2, ETSI, European Telecommunication Standards Institute standardization activity for NFV standards. This NFV reference architectural framework is standardized by ETSIH. So the left-hand side, I have explained to you just before. Right-hand side is a manual. Manual is management and orchestration. So it consists of orchestrator, VNF manager, and virtualized infrastructure manager, VIM. Orchestrator case performs management for lifecycle and component management of network services. VNF manager is performing actual lifecycle management, such as creation, verification, software update or change, scaling up, scale down, restoration, and deletion of VNF instances. Finally, the VIM, Virtualized Infrastructure Manager, manages actual resources and also virtualize such hardware resources into virtual resources. So VNF infrastructure having actual computing virtualization, storage virtualization, network virtualization. Those virtualized resources are constructed for VNF. Subsection 3, open source project, NFV. Now we have 3 kinds of open source project for NFV. The first one is OpenStack, second one is OSM, open source manual. Third one is OP-NFV, Open Platform for NFV. So OpenStack is providing a cloud environment to virtualize network environment. Secondly, OSM provides manual management and orchestration function. And finally, OP-NFV provide the environment to develop and testing of NFV component to facilitate the NFV deployment. So this figure shows OpenStack. So OpenStack provides the infrastructure. So bare metal servers are used to virtualize the function. Also, the container can be used. Okay. And the object storage, file storage, block storage can be used. And other dashboard, GUI monitoring tools can be used. So OpenStack has a lots of project. So web front end, Horizon, API Praxis is 2 API are developed. Also workload provisioning, application lifecycle orchestration. There are tons of projects. So computing case, Nova, June, the Quinlin projects are under development. And also networking case, SDN case, Neutron, load balancing case, Octavia, DNS is designate, okay? Bare metal and the storage case also their own project. Secondly, OSM. OSM, I mentioned, provide manual functionality, especially implement a generic VNF manager. So this VNF manager has 4 functionalities: resource orchestration, secondly, VNF configuration agent, monitoring component, and service orchestration. So you can see, so human users using this kind of GUI interface deliver some configuration, and then VNF manager process that configuration, and then actually maintain, also perform lifecycle management of VNF using this kind of structure. Finally, OP and NFV case, it provides ecosystem for developing and testing reference NFV platform. So developer are making new NFV component. On top of this NFV testing platform, we can test integration, functionality testing, also new features can be tested. Testings can be done using regression. So we can speed up the deployment of NFV. Third topic is cloud-based security service systems. Subsection 1, cloud-based computing systems. So we have many kinds of smart areas, such as smart IoT, smart load, smart campus, smart grid, and smart electricity business. So to support these kinds of cloud-based computing systems, three main technologies are required. The first one is software-defined networking, SDN. Secondly, network functions virtualization, NFV for cloud instantiation and management. Finally, the service function training, SFC, can be used to construct actual network services using multiple VNFs. This figure shows security service management. Okay, some user traffic is packet delivered, and then some malicious traffic is delivered to SDN controller delivered to actual firewall web filter, and using machine learning can detect this one is some malicious or suspicious and drop. Secondly, IoT device management can be done using this kind of cloud-based system. So IoT devices sensing and monitoring data will be delivered to IoT monitor, and software integrity checking and activity monitoring can be done using these kinds of monitoring traffic. And also, smart electricity business management can be done. So, such as many people on top of roof, we have a solar panel. We save solar energy, and then using electricity broker on top of a VNF environment, and then we can negotiate the sales of the extra the energy. Also, we can deliver that energy to the factory. Subsection 2, IETF, cloud-based security standardization activity. First of all, I2NSF stands for Interface to Network Security Functions. The background is the flexible and the scalable provisioning of security services on top of NFV environment is required, because we want leverage the existing physical network functions based on middle box, and also virtualized function such as virtual network functions can be harmonized. So because of that, 7 years ago, IETF, Internet Engineering Task Force, de facto Internet standardization body in the world, IETF, I2NSF working group started to make standard interface to network security functions for cloud-based security systems. Now, this figure shows a cloud-based security service system with the I2NSF. Left-hand side is a configuration of I2NSF-based cloud security service. Right-hand side, actual the framework of I2NSF framework and actual implementation of I2NSF on top of NFV environment. So, for example, administrator deliver high-level policy about company in a smart building to I2NSF framework using consumer-facing interface, and the security controller translate into low-level policy enforced by network security functions such as firewall, IDS, and antivirus, and DPI, deep packet inspection. And also vendors, management system, registers its own NSF with NSF capability and access information such as IP address into security controller. and the security controller can translate high-level policy delivered by I2NSF user using NSF capability information, and translate the high-level policy into low-level policy understood by NSFs. So these kinds of I2NSF framework is implemented on top of NFV architectural framework. So the I2NF user can be implemented OSS and BSS. OSS means operating support system. BSS stands for business support system. And the security controller and the vendor's management system or developer management system can be instantiated using EM. EM stands for element management. And also each NSF can be instantiated using VNF on top of this NFV environment. So we published IBCS, intent-based cloud services for security applications, in IEEE Communication magazine. Please take a look at this paper. So I2NSF framework architecture. So you can see left-hand side, the video client want to get video streaming service from right-hand side, the video server. So in that case, we import security configuration using I2NSF framework. I2NSF user such as video component controller, service orchestrator, and administrator deliver high-level policy into low-level into security controller. Security controller translate high-level policy into low-level security policy that is understood by the each NSF. And develop management system registered capability and access information such as NSF IP address with the security controller. Security controller stores such capability and access information into each NSF database. So NSF database can be used for security policy translation. So this kind of framework having I2NSF component, I2NSF user, security controller, developer management system, and NSF. And standard interfaces, 3 interfaces, consumer-facing interface, registration interface, and NSF-facing interface are explained following RFC. RFC stands for request for comment. IETF standard name is RFC with some number. So RFC 8329 is about framework for I2NSF. Please visit to this link. So I explained each interfaces, registration interface, consumer interface, and NSF interface. So registration interface can be used to register NSF capability and access information into security controller. And the consumer-facing interface is used to deliver high-level policy from I2NSF user to security controller. NSF-facing interface is used to deliver low-level policy from security controller to appropriate NSFs. This slide shows standardization activity at I2NSF working group. I2NSF working group has published 2 RFCs. The first one is I2NSF problem statement and use cases. Second one is framework for I2NSF. First RFC case, I'm also a co-author for this one. So explain the problem motivation and the problem statement for I2NSF, and then the specific use cases for I2NSF. And the second one is explain the components and interfaces in the I2NSF framework. So you can visit this website to get standards document from IETF. This slide shows I2NSF working group document. So among 7 documents, 6 documents are managed by my lab. I am the editor of those 6 above 6 draft. Applicability draft, capability data model, consumer-facing interface data model, and NSF-facing interface data model, and NSF monitoring data model, and registration interface data model. Those are, most of them are reviewed by young doctor, and also young doctor means the expert to review young data model for interfaces. And the first applicability is already published as RFC, waiting for resolution and the publication report data model draft become the RFCs. This slide summarizes current status of our draft. Okay, so applicability is already published, approved RFC. So in RFC edit queue, the final the waiting means the report normative references draft should be published before this draft becomes RFC. So capability is, data model is a basic the young data model for other following four interfaces: consumer-facing interface, NSF-facing interface, registration interface, and monitoring interface data model. And also, the Spain, some university, they are standardized SDN-based IPsec flow protection between I2NSF security controller and NSF, or between two NSFs to establish IPsec session. And the other individual draft is recently I proposed the new extension for I2NSF framework for security management automation for cloud-based security services. And this translator draft also developed, and this one will be standardized after the chartering of our I2NSF working group. And NFV architecture case, this draft case, we propose a container consideration for I2NSF. And the first one is Telefonica, the Diego Lopez. He is NFV research group chair. So they are working for remote attestation to procedure to check the whether NSF is working well according to each software configuration or not. So I2NSF can be used for those cloud-based security service systems, such as vehicle IoT, smart home, smart company, smart campus, cellular networks, and data center. So three technologies are important: SDN, SFC, and FV. So first one, the SDN and the I2NSF. So you can see, so upper part is I2NSF framework, lower part is SDN. Switch controller means SDN controller is connected to southbound interface such as OpenFlow. So SDN switch here, right? So security controller deliver the loyal policy for the firewall service using SDN switches. Okay, so in that case, NSF-facing interface used. And the more complicated firewall or DPI security service can be configured using this NSF-facing interface with the firewall, web filter, DPI, etc. So this is another aspect of I2NSF framework with SDN. So the simple, the filtering service can be done SDN switches. More complicated filtering over firewall service can be done NSF. Okay. Secondly, I2NSF framework with SFC. So we want to provide a chaining service, such as one packet belonging to one flow, penetrate first over a firewall, secondly web filter, and finally DPI inspect this packet. So to provide that kind of chain of NSF, we make this kind of rule. can be done using I2NSF and SFC. So SFC providing classifier construct actual service function SFFS, and SFF means actual the forward according to service function path using NSH network service header of packet. Third one is I2NSF framework with NFV. So this figure shows how to construct I2NSF on top of NFV environment. So I2NSF user deliver high-level policy over consumer-facing interface. So security controller checks its NSF database. If there is no NSF learning for that kind of high-level policy, so deliver some request, calling message to vendor's management system. And the vendor management system instantiate appropriate NSF interacting with the manual system right-hand side, and then NSF is launched. And then that access information and capability delivered to security controller. Security controller configured with the low-level policy to enforce required security service. Security policy translation is a very important function because to provide intent-based security service, specification of a scheme of security policy translation in I2NSF framework is required. So this document is updated nowadays. Status current individual draft. I believe this document will be adopted as a working group draft next year. So first of all, user or administrator specify high-level policy such as I won't block my son's computer from malicious website, some game website or adult website. So in that case, actually my son's computer using some specific IP addresses and malicious website specified specific URL, harm.com and illegal.com. So specification of high-level policy is more convenient for user or administrator, but actual security enforcement based on specific IP address and specific URLs. The question is how to translate from high-level policy into low-level policy. So in the past, we used using XSLT. This is a popular method, XML-based policy translation based on hard mapping. So the limitation is the difficulty of security policy construction maintenance. So as a result, we invented automata-based policy translation from compiler theory. So it is easy to construct the security policy. Also, it is efficient to maintain new policy over augmented policy. This figure shows security policy translation, such as in a company, employee cannot access SNS website. SNS website specified Facebook and Instagram, and employees' computers' IP addresses are the range is this 10.0.0.2, 10.0.0.10, something like that. So that kind of policy delivered by item user by a consumer-facing interface, and according to 3 steps: data extract, data converter, policy generator, and the low-level policy translate, such as employees' IP address are translated, and also SNS website translated into specific URLs. This figure shows the more specific translation procedure. So the right-hand side up is my son's PC cannot access a malicious website, block. So low-level policy case, my son's PC translated specific IP addresses of my son's personal computer or laptop or smartphone, and malicious website translated into specific URLs, harm.com and illegal.com, and packet will be dropped by the SDN switches or firewall, okay, network security function. And then extractor means high-level policy XML file given and then extract important data, block web, Sun's PC, and the malicious, and the block is high-level policy data using this DFA. DFA is determinative finite automata using this treble, using tag, and then extract data and then trebles back and then take out Sun's PC, malicious, and the block. And second step is a data convert, such as high-level policy data are translated into low-level policy data, such as son's PC translate into IP addresses of my son's PC, and the malicious is translated into specific URLs, harm.com and illegal.com. Okay, and then using machine learning such as decision tree, we can take a look at the data, and then we can select the logo keeper, web filter, DDoS attack mitigator. So in our case, based on URL, this important field, we select logo filter, keeper, and web filter are selected using decision tree. And then the third step is generator. Generator construct XML file for NSF facing interface. So using context-free grammar in the automata theory, so based on low-level policy, constructed low-level policy XML using the CFG. Okay, so in detail description is explained in our draft. Please take a look at our security policy translation draft. Okay. Subsection 3, open source project for I2NSF. Okay, so subsection 3, open source project for I2NSF. This picture shows the IETF hackathon. So IETF 104 hackathon. So, okay, I think this is our I2NSF hackathon project team table, and this is my student. And this is the poster I2NSF project, okay, 108 hackathon. So July 2020. So the goal is we re-establish I2NSF environment. Also, we try to set up security policy translation. So the hackathon project is usually try to reflect the latest revision of our draft, such as capability data model, consumer face interface, etc. So this is the network topology for hackathon project. So this is the configuration, items to user, this is a security controller, DMS, okay, development management system, and firewall, time-based firewall, and the web filter. They are connected using service function chaining SFC. And the employee try to access during work time. They cannot, because the time-based firewall is configured. So they cannot access SNS website. Right side is open source information. For example, OS is Ubuntu 16.04, and we're using netconf confd, and the MySQL for database, OpenStack for cloud. Suricata is for web filter, and LetsConf is used for consumer-facing interface to deliver high-level compilation XML file. And minimum specification for OpenStack, so RAM, storage, CPU are like that. What we got done, so we restored the I2NSF framework on top of OpenStack, web-based I2NSF user, and the console-based security controller, and DMS, and the security policy translator. And also we reflected the latest revision of Yang data model. What we learned, so we recognize the necessity of security policy translator to support the following features for IBM intent-based networking. So first one is automatic mapping between high-level Yang module and low-level Yang module attributes. Secondly, installation of low-level Yang production rule to generate context-free grammar XML file for low-level policy. And the next steps, so we will reflect the latest registration interface, Yang data model, and also we will implement I2NSF monitoring, Yang data model, and finally we will enhance the security policy translators with the above the features. So this is a description of our team member. I was the champion leader of this hackathon project, and my student Patrick, Jaehong, Joseph, and the participant from other university, Sungsil University and Gyeongbuk National University, and also some company member, Benson. So right side there is an open source project. You can get our open source code, and also right hand side there is a video demonstration clip. This is a demonstration for I2NSF hackathon project. So I will show our demonstration. So this hackathon project performed by H3 and Sangkyungan University SKKU for IETF 105 hackathon in Montreal in Canada. So this is a controller, this is a dashboard. So dashboard case, we register registration interface is used to register web filter and time-based firewall. First of all, we register firewall, virtual firewall, okay, using registration interface. Okay, and secondly, we register web filter based on Surikata. So Surikata is originally developed IDS IPS. We modified for web filter. So we registered using registration interface XML file like this, okay? So we registered. So capability of the firewall and web filter with the security controller. And this is a consumer-facing interface. So we define employee IP addresses, and also we specify devices registration, such as all denied case or IP addresses denied. And URL registration case, SNS website is Facebook and Instagram. And then we employees, okay, start IP address and then ending IP address is specified. So using consumer-facing interface, we specify, okay, blocking for SNS website, such as employee cannot access during work time from 9 a.m. to 6 p.m. And also, case one is okay, web filter. Secondly is time-based firewall. So off time or block means after work times, such as from 6 p.m. through next 9 a.m. So all traffic are discarded. So based on that kind of security policy, security controller translate into low-level policy. So now we can access, right? But after enforcement of security policy, we can see the employee cannot access those kinds of SNS website or other website according to cases. So we created policy created a network configuration. So you can see virtual firewall and web filter Surikata, they are connected using service function chaining. This is OpenStack dashboard. We can configure the switch and also the network security function can be connected using SFC. So NS-facing interface use deliver low-level policy into appropriate NSF such as a firewall and web filter. So we enforces require the policy. And then we can demonstrate web filter and time-based firewall service. So now we can see, so low-level policy is configured by NSF, and the user try to connect, okay, Google, and they cannot access Facebook, Instagram, or websites are filtered because time-based web filter performed, okay? The secondly, time-based firewall case after work time, after 6 p.m., all traffic are dropped. So those are our hackathon project demonstration. So I explained the demonstration for I2NSF hackathon project. So our project is an open source project in GitHub. So you can visit this GitHub link. You can get our source code. So these photos are IETF 103 I2NSF hackathon project. So my student and the Sungsil University student, we collaborated for this I2NSF hackathon project, and we took some memory photo, and also some Chinese engineer visited our booth, our poster. My student and the Sungsil University student explained the questions, okay, about our hackathon project. This is okay, the award shot. So among 21 teams, we got 3 top teams. Okay, we got best award, the 103 hackathon, okay, project. So in the middle is hackathon chair, Charles Eckers from Cisco. So usually hackathon project is Saturday and Sunday before the preliminary meeting of IETF. So the Monday afternoon, some of the team voluntarily demonstrate the hackathon project and share our experience during hackathon. And my team and other colleague or professor, we took picture with the hackathon chair. So conclusion, in this talk, I explained network softwareization and the cloud-based standardization activities such as software-defined networking, SDN, network functions virtualization, NFV, and the cloud-based security service systems. So we can see based on those network softwareization and the cloud, we can provide the various domains, such as security services, IoT device management, and the smart electricity business. So this is references used by this talk. So you can refer to specific link for your detailed information. Thank you for your attention. If you have question, you can contact by my email address. Thank you.